Okay, so you get that. And if these two are equal, then no, the answer is 0. All right. How about the expectation value of s squared? Well, you know the 2 by 2 matrix for that operator. It's 3h bar squared over 4 times this matrix. Here's your bra and ket, just the same as here. Okay. So again, just simple matrix multiplication, work it out, and you get this, right? But c1 squared plus c2 squared, because these spinners are orthonormal, okay? So c1 squared plus c2 squared is just 1. So the average value of this expectation value, same thing, is 3h bar squared over 4. All right. Now we've talked about this a little bit before. Keep talking about the z-axis, but what does that actually mean? Like if you go into a lab and some student comes in and says, show me the z-axis. I keep reading about the z-axis in the textbooks and the videos. Where's you're talking to the professor experimentalist. Show me your z-axis. And the experimentalist will just say, well, my z-axis is the direction that I choose to measure the components by. If I measure the components by the orientation of a very strong magnetic field, for example, then that orientation of the magnetic field, that would be your z-axis. Okay, and then yeah. So in other words, it's experimentally determined. So okay, that's what it's saying here. And no matter what your z-axis is, no matter how you define it experimentally, for the eigenvalues h bar over 2, you will only get 2 orientations. Right? It'll be either, the eigenstate will be either spin up or spin down, relative to that orientation, that z-axis. All right. Now, interestingly, imagine before you perform the measurement that the particle going into, let's say, going into a magnetic field. Later we'll be more concrete and we'll talk about something called a Stern. That's a German physicist, Stern, Gerlach. 2 German physicists, Stern and Gerlach. They were sending particles through strong magnetic fields. And imagine, and to see whether they would deflect up or down. In other words, measuring whether the spin on the system was up or down. So imagine that the state of the system, the particle, let's say, before it goes in, before the measurement, before it goes into the magnetic field to get deflected up or down. Imagine that incoming state before the measurement is an eigenstate itself. Then, so long as the measurement, how can I put this? To create the eigenstate to start with, you do a measurement, let's say, and say the particle gets deflected up or down. And if it gets deflected up, you block that. You're not interested in that. You only take the particles that deflect down, and therefore you know the state of that particle. It's one of the eigenstates, because the orientation is either up or down. Now we block out the upper ones, let's say. So we know the state going into the second measurement now. And but for the second measurement, our z-axis, in other words, the orientation of the magnetic field, let's say, has been shifted by an angle theta. Well, then even if the state coming in was an eigenstate for some z-axis before, if you then measure it again with a different z-axis, call it z dashed, which is has an angle theta different in orientation from the z-axis for your first measurement, again for the z dashed, the second measurement, you will still get only two components, the spin up and spin down, which is interesting. That's what I'm saying here. And this kind of talk that I've just been saying is a lead-in to, but we won't do it this course, unfortunately. But it's something to really look forward to in the next quantum mechanics course. That might be about a year or so before I do it. At M1 level, when we come to talk about the famous Bell inequalities, which I've mentioned this before, but refresh your memory. Bell's inequalities provide an experimental test between Einstein's ideas and quantum mechanics. Now, Einstein hated quantum mechanics. He hated the lack of determinism of quantum mechanics. And so Bell was able to, using this kind of spinor, two-dimensional matrix operator, type terminology and mathematical tools and so on. So we're getting close to it. And he was able to come up with some mathematical quantities, inequalities, which actually tested, like quantum mechanics predicted one thing, and Einsteinian-like, in other words, local hidden variables. What that means is hidden variables, like extra variables beyond the variables of quantum mechanics, which allow you to restore determinism. In other words, you can predict, well, hypothetically, you could, that's the theory behind hidden variables. These extra variables, which seem hidden to us for the moment, they then allow the deterministic prediction of the behavior of a single particle, right? So you can predict whether it goes up or down when it deflects through a magnetic field, or in the Stern-Gerlach experiment, whatever. You could do that kind of thing. And local, there's no such thing as non-locality, or the same thing, entanglement. Einstein hated entanglement. He called it, well, I've mentioned this before, but in German, spukhafte Fernwirkung, which means spooky, ghost-like, spooky action at a distance. Fern is German word for far or distant. Wirkung, action, interaction, distant interaction. That's spooky, that's ghost-like. That's the way he labelled non-locality or entanglement. So Bell's inequalities were able to distinguish. There was a predicted difference between these two philosophies, these two different models, the quantum mechanical model and the Einsteinian local, none of this non-local business, which Einstein loathed. Physicists then got very excited. Bell came out with these inequalities in the 60s. First experiments were started to get done in the 70s, but there are lots of loopholes. The early results showed quantum mechanics, the prediction of quantum mechanics were valid, and that it seemed that non-locality was valid, was real. But there were loopholes, and people said, "Oh, yeah, but they picked holes in the experiments." And then the Frenchman ASPECT came along, and in the early 80s he did a far more definitive experiment, which seemed to show that, pretty convincingly, I won't go into details, but showed pretty convincingly that non-locality is just a fact of nature, which is pretty weird. So you'll have to wait till the next course to actually derive these famous Bell inequalities, and that, I hope, will get you thinking on the nature of non-locality. How can nature be like that? Indeed.